Hi friends, welcome back to the channel, and today we are planning to solve a problem which was asked in GATE 2020. It's a 2 mark problem. So I request you to read the problem very carefully. It's a fairly short question, so you can read it on your own and then try solving on it on your own. If you're stuck at somewhere, then come back and watch rest of my video. So going ahead, there are a couple of ways in which we can solve this problem. I will discuss the both ways in this short video. So first, let's get started with the first method, which is the energy method. So the energy method makes use of Castigliano's theorem. Castigliano's theorem states that you write the total strain energy as a function of your loadings and displacements. Then you take the partial differential of that strain energy with respect to a force with respect to P in this particular problem to get the deformation at the point along the direction in which P is acting. This is called the generalized force, and this is called the generalized displacement, and there are a lot of other things. So the first step is write an expression for the total strain energy, then take the partial derivative of strain energy with respect to the external force, and that will give you the displacement at that point along the direction of the externally applied load. Make sense? So what I've drawn over here is the free body diagram of the beam alone. As there is a P, which is an external load, then there is a force K times the displacement at x equal to L. K is the stiffness of the spring, and V at bracket open x equal to L bracket close represents, or this whole quantity represents the displacement at x equal to L. Makes sense? So these are the two forces acting at the end of the beam. What I'm interested in is finding out why I'm interested in the bending moment. Is the reason is pretty simple, because the total strain energy in this system is composed of two things. One is the bending energy or of the beam, and then there will be some energy stored in the spring as well, which will be given by half K times V0 square, where V0 is the amount by which this point moves. Make sense? Then the strain energy stored in this portion of the beam will be given by this expression, m square divided by 2 EI dx, where m is the bending moment, resultant bending moment acting at each of these sections. E is the Young's modulus, I is the moment of, or EI together can be called as the flexural rigidity, I is the moment of inertia, area moment of inertia. Makes sense? So there are two components. There is another component as well. Because of the shear force, there will be a shear energy also stored in the beam, but it is very small, or which it is very negligible in comparison to the bending energy. So let's go ahead and try to get an expression for the resultant bending moment acting at a section which is at a distance x from this end. So now I'm trying to take the moments about the point A. I'm assuming that the bending moment is m at that section. Then once I impose this criterion that the summation of moments about the point A should be 0, then I end up with the expression for the bending moment acting at that section, which is a function of x. Makes sense, because as x increases, the bending moment also increases. But this portion is a constant, because this portion is not going to vary along x. So I'm giving it a new notation, C1. So whatever quantity is there in the bracket, I'm calling it with a new variable named as C1. Now as a next step, I'm going ahead and evaluating what is the bending energy, strain energy stored because of the bending deformation. That amounts to something like this. It's pretty straightforward. Simply plug and check. There is another component of the strain energy which comes from the spring, which is simply half kx square. It is also a very well known formula. Once we take the partial derivative of this strain energy with respect to the load, then again we will get the displacement at that point. This comes from the Castigliano's theorem. It's a very handy theorem, because most of the time don't have to bother too much about the sign conventions. We don't have to bother too much about the orientation of axes and all those things. It's a really it's a really handy tool to have and to master. Believe me, even once I start working also, it comes handy in certain situations. It gives you, or it helps you to solve very complex problems. Once you do that, you arrive at here. This is the term coming out of the partial derivative, and this is the coming from here. Now again, simply rearranging the terms, we will get an expression for the tip displacement of the beam as shown over here. Make sense? That's clear. A little bit of consideration will tell you that when you have a spring there, for a given load the displacement decreases, isn't it, as per this formula? That makes sense. So this kind of interpreting the answer will help you to eliminate a few options. I can simply say, had this expression been like this, oh, I'm talking about the quantity in the bracket, sorry, there is an L cube, this expression is wrong, because I can definitely tell this answer is wrong. Why? Because as k increases, the displacement goes up, which is counterintuitive, because the more stiff the spring you have in at that location, less will be the displacement for a given p. So this kind of physical appreciation, or as just having a look at your answer, or an appreciation of your answer towards the end or after solving the problem, will help you in a lot many ways. Now, in short, I will explain the method 2 also. Method 2 doesn't make use of Castigliano's theorem, but it makes use of a very common understanding that first what you do is you convert the system into two systems. Now we have a spring, then we have a beam. Now the beam is a cantilever with a tip load of P minus R. While the spring is very simple, it's a spring, it is applied upon by an external force little r. There is a compatibility constraint, or there is a constraint that governs the system, which goes like this. Whatever be the downward displacement of the beam, the same will be the deflection felt by the spring also. Make sense? So if in this case the spring moves down by little r by k, very simple, and for a cantilever which is having an end load of P, we know the equation is PL cube divided by 3EI, and in this case the end load is not P, it is P minus R L cube divided by 3EI. So this comes from the compatibility constraint or the displacement constraint of the problem. From this we can solve for capital R. Make sense? Then you can plug in either of these formulae to get the displacement at the point, at the end point. This seems fairly easy, but I wanted to tell you Castigliano's theorem also. That's why I preferred the method 1. So now solve for capital R. Solve for capital R. Then plug in, if I call this equation 2, then plug in R, plug in equation 2. Okay, so this is how we evaluate the displacement from method 2. Thanks for watching the video. I think you got a little bit of information regarding the Castigliano's theorem, and then how you can do this problem in both ways. Okay.